The universe stretches out before us, vast and quiet. Tonight, we explore one of the most peaceful mysteries in all of cosmology, the Great Silence, the gentle question that has puzzled scientists for decades. In a galaxy containing hundreds of billions of stars, why do we hear nothing but the soft static of empty space? This is a calming journey through the Fermi Paradox, a meditation on cosmic solitude, and an exploration of why the darkness around us might be exactly as it should be. Settle in as we drift through the quiet corridors of this ancient mystery, examining the mathematics of loneliness, the filters that make awakening rare, and the comforting possibility that we might be the first candle lit in a universe just beginning to stir. There are no alarming revelations here, only the soothing rhythm of scientific inquiry and the peaceful acceptance of our place in the silent cosmos. In 1961, astronomer Frank Drake developed a simple equation to estimate the number of active communicative civilizations in our galaxy. The Drake equation remains one of the most elegant frameworks for understanding our cosmic loneliness. It begins with the rate of star formation in the Milky Way, approximately 2 new stars each year, a steady pulse that has continued for billions of years. The equation then multiplies this by the fraction of those stars that have planetary systems. Current observations suggest this number is remarkably high. Perhaps 80 to 90% of all stars host at least one planet. The next variable considers what fraction of those planets could actually support life, those within the habitable zone where liquid water can exist on the surface. Conservative estimates place this around 20%, though some calculations suggest even higher numbers. Then comes the fraction of suitable planets where life actually appears, a number we cannot yet determine with certainty. Following that, the equation asks what fraction of life-bearing worlds develop intelligent life capable of technology. On Earth, this took approximately 4 billion years, suggesting it may not be an easy transition. The next factor is the fraction of civilizations that develop technology capable of releasing detectable signs into space, radio transmissions, light signatures, or other electromagnetic signals. Finally, the equation considers how long such civilizations remain detectable, whether they last for centuries, millennia, or millions of years before falling silent. When Drake first calculated his equation with optimistic values, he estimated there might be thousands of detectable civilizations in our galaxy at any given time. Yet when we point our radio telescopes toward the stars, we encounter only silence. This discrepancy between mathematical expectation and observational reality forms the foundation of the Fermi Paradox. The equation itself is less important for its answer than for the questions it raises. Each variable represents a filter, a hurdle that must be overcome. The profound silence we observe suggests that at least one of these variables must be far smaller than we initially hoped, or that we fundamentally misunderstand something about the nature of technological civilizations and their desire or ability to communicate across the vast distances of space. Our galaxy, the Milky Way, contains between 200 and 400 billion stars, spread across a disk approximately 100,000 light-years in diameter. These numbers are so large they become abstract, losing their meaning in the vastness they represent. To understand the scale, consider that if each star were a grain of sand, the Milky Way would contain enough sand to cover all the beaches on Earth several times over. The galaxy rotates slowly, completing one full rotation every 225 million years at our solar system's position. We orbit the galactic center at approximately 515,000 miles per hour, yet the distances are so immense that our motion seems imperceptible against the fixed stars. Within this vast collection of suns, Current estimates suggest there are at least 100 billion planets, and potentially as many as 1 trillion when including rogue planets that drift through interstellar space without a host star. Many of these worlds orbit within their star's habitable zone, that temperate region where conditions might allow liquid water to exist. The sheer abundance of potentially habitable real estate makes the silence even more puzzling. If even a tiny fraction of these worlds developed life, and an even tinier fraction of those developed technological civilizations, the galaxy should be teeming with activity. The distances between stars, while vast, are not insurmountable barriers to communication. Radio waves travel at the speed of light, meaning a signal from a civilization 1,000 light-years away would take 1,000 years to reach us, but it would reach us. Our own radio transmissions have been propagating outward for nearly a century, creating an expanding bubble of human-generated signals now encompassing thousands of star systems. If other civilizations have been broadcasting for thousands or millions of years, their signals should be detectable across significant portions of the galaxy. Yet our most sensitive instruments detect nothing but the natural radio emissions of cosmic phenomena, pulsars spinning in the darkness, the whisper of hydrogen clouds, the background hum of the universe itself. The Milky Way, for all its stellar abundance, remains profoundly quiet. The universe is approximately 13.8 billion years old, a span of time difficult to truly comprehend. Our Sun and solar system formed much later, about 4.6 billion years ago, from the remnants of earlier stellar generations. This means the universe existed for over 9 billion years before our world came into being. During those 9 billion years, countless stars were born, lived their lives, and died. Many of those stars formed billions of years before our Sun, and many hosted planetary systems of their own. This temporal head start is crucial to understanding the Fermi Paradox. If life is a natural consequence of suitable conditions, then civilizations should have emerged on older worlds long before Earth even existed. Some of these civilizations could be billions of years more advanced than humanity. The technological gap between such ancient civilizations and our own would be incomprehensibly vast, like comparing a modern computer to the first stone tools. Even civilizations that emerged just 1 million years before us would possess technology and capabilities that might appear magical from our perspective. 1 million years is a mere blink in cosmic time, yet it represents 50 times the entire span of recorded human history. The question becomes unavoidable: where are they? If intelligent life is common, the galaxy should have been colonized long ago by one of these ancient civilizations. The Milky Way is approximately 10 billion years old, providing ample time for expansion, exploration, and the establishment of a galactic presence. Yet we see no evidence of such expansion, no megastructures surrounding distant stars, no obvious signs of stellar engineering, no directed signals attempting to make contact with emerging civilizations like our own. The sky remains as it has always been, a tapestry of natural phenomena following the predictable laws of physics. This temporal paradox deepens the mystery. It is not merely that we fail to detect other civilizations in our current era, but that we see no evidence they have ever existed throughout the entire history of the galaxy. The silence extends backward through billions of years, suggesting that whatever prevents us from detecting alien civilizations is not a temporary condition, but something fundamental about the nature of life, intelligence, or technological development in the universe. Mathematician John von Neumann proposed a theoretical concept that makes the silence even more puzzling: self-replicating machines. A von Neumann probe would be a spacecraft capable of traveling to another star system, using the resources it finds there to create copies of itself, which would then travel to additional star systems and repeat the process. The mathematics of exponential growth make this concept particularly relevant to the Fermi Paradox. Even with relatively slow spacecraft traveling at just 10% of the speed of light, a single self-replicating probe could theoretically explore and colonize the entire galaxy in approximately 2 to 10 million years, depending on how long each replication cycle takes. 2 million years sounds like an enormous span of time from a human perspective, but it represents just 0.02% of the galaxy's age. If any civilization in the history of the Milky Way had launched such probes, even billions of years ago, their descendants should be everywhere by now, including our own solar system. The concept does not require faster-than-light travel or any physics beyond our current understanding. It simply requires patience and the initial investment of creating the first probe. Once launched, the exponential nature of replication does the rest. One probe becomes 2, 2 become 4, 4 become 8, and within a relatively short time on cosmic scales, millions of probes spread throughout the galaxy like seeds on the wind. These probes need not be large or complex. They could be small, efficient machines designed for one purpose: to travel, replicate, and continue the expansion. Some variations of the concept suggest they might also gather information, sending data back to their civilization of origin, creating a galaxy-spanning network of sensors and observers. Yet we detect no such probes in our solar system. No ancient automated spacecraft orbiting in the outer reaches. No self-replicating machines harvesting asteroids for raw materials. The asteroid belt, rich in metals and minerals, remains untouched by any obvious technological presence. This absence is telling. It suggests that either self-replicating probes are not a strategy employed by advanced civilizations, or there are no advanced civilizations to employ them, or they exist but remain deliberately hidden from our detection. Each possibility carries profound implications for our understanding of intelligence and technology in the universe. Since the 1960s, humanity has been listening to the cosmos with increasingly sophisticated radio telescopes. The search for extraterrestrial intelligence, or SETI, has scanned thousands of star systems across multiple frequencies, searching for any signal that might indicate technological activity. The results have been consistently disappointing. The universe produces enormous amounts of natural radio emissions. Pulsars emit regular pulses as they rotate. Quasars blast radio waves across billions of light years. Hydrogen clouds whisper at specific frequencies. Lightning on Jupiter creates static. All of these signals follow predictable patterns consistent with natural phenomena. What SETI searches for are artificial signals, transmissions that show signs of intelligent design, narrow-band frequencies, repeating mathematical patterns, or modulations that suggest information content. In over 60 years of searching, only one signal has ever generated significant excitement. In 1977, the Big Ear Radio Telescope detected a strong, narrow-band signal that lasted 72 seconds, dubbed the wow signal after the astronomer who discovered it wrote that word on the printout. Despite numerous attempts, the signal has never been detected again, and its origin remains unexplained. It stands alone as a tantalizing mystery, neither confirmed as artificial nor explained as natural. Beyond that single anomaly, the silence is absolute. The galaxy produces no obvious technological signatures, no repeating patterns, no attempts at contact, no leakage from alien television broadcasts or radar systems. The absence is so complete that some scientists have begun to question whether radio communication is even the method advanced civilizations would use. Perhaps we are listening for smoke signals while they communicate through means we cannot yet imagine or detect. Or perhaps the silence is exactly what it appears to be: genuine absence. The possibility that we are alone, or at least alone in our corner of the galaxy during this particular epoch, becomes harder to dismiss with each year of negative results. The silence is not merely the absence of signals, but the absence of any obvious technological modification of the cosmos. When we look at distant star systems, we see nature operating according to physical laws. We do not see stars dimmed by megastructures harvesting their energy. We do not see unusual chemical signatures in planetary atmospheres suggesting industrial processes. We do not see the infrared excess that might indicate waste heat from massive computational systems. The universe appears pristine, untouched by intelligence, a garden without gardeners. The concept of the Great Filter attempts to explain the Fermi Paradox by proposing that somewhere between non-living matter and galaxy-spanning civilizations, there exists an extremely difficult step, a filter so challenging that very few, if any species, ever pass through it. This filter could exist at any point along the evolutionary pathway. It might be the initial emergence of life from non-living chemistry, a step that may be extraordinarily rare despite the abundance of suitable conditions. It might be the development of complex cells with nuclei, a transition that took billions of years on Earth and may have required an unlikely symbiotic merger between simpler organisms. It might be the emergence of intelligence itself, which appeared only once among millions of species on our planet. Or it might lie ahead of us, a future challenge that technological civilizations typically fail to overcome. The location of the Great Filter has profound implications for humanity's future. If the filter lies behind us, in our past, then we are extraordinarily fortunate to have passed through it, and our future might be relatively secure. Perhaps the origin of life is so improbable that Earth is one of the only places in the galaxy where it occurred. Perhaps the evolution of intelligence is so unlikely that we are a cosmic rarity. These possibilities, while making us special, also suggest that the galaxy is largely empty and available for future expansion. However, if the Great Filter lies ahead of us, the implications are more troubling. It would suggest that something about technological civilizations makes them inherently unstable or self-limiting. Perhaps advanced technology inevitably leads to self-destruction through warfare, environmental collapse, or the creation of dangerous artificial intelligence. Perhaps there are physical limits to expansion that we have not yet encountered. Perhaps something about the nature of advanced civilization causes species to turn inward or transcend physical existence, removing themselves from the observable universe. The silence of the cosmos does not tell us where the filter is located, only that it exists. Every observation that fails to detect alien civilizations strengthens the case that at least one step in the pathway from matter to spacefaring civilization is far more difficult than we might hope. The filter acts as a cosmic sieve, allowing very few, if any, to pass through to become the galaxy-spanning civilizations that should be obvious to our telescopes. The transition from non-living chemistry to living organisms remains one of the most profound mysteries in science. Despite decades of research, scientists have not yet created life from scratch in the laboratory, nor do they fully understand the precise sequence of events that led to the first living cells on Earth. Life requires several components working in concert: a metabolism to process energy, a membrane to separate the organism from its environment, and a genetic system to store and transmit information. Getting all of these components to emerge simultaneously from non-living chemistry may be extraordinarily difficult. On Earth, life appears to have emerged relatively quickly after conditions became suitable. The planet formed 4.6 billion years ago, and evidence suggests life existed by at least 3.8 billion years ago, possibly earlier. This rapid appearance might suggest that life emerges easily given the right conditions. However, it is equally possible that Earth got extremely lucky, and that we exist to observe this outcome precisely because it happened here, a selection bias that prevents us from knowing how typical our experience might be. The chemical processes that lead to life require specific conditions. Liquid water serves as a solvent for chemical reactions. An energy source, whether sunlight, chemical gradients, or geothermal heat, drives the system away from equilibrium. A supply of organic molecules provides the building blocks. Earth had all of these, but having the ingredients does not guarantee the outcome. The step from complex organic chemistry to self-replicating systems capable of evolution may require conditions so specific or coincidences so unlikely that it rarely occurs. Some scientists have proposed that life might have originated elsewhere and been transported to Earth via meteorites, a hypothesis called panspermia. While this would explain how life arrived on our planet, it merely pushes the question of origin to another location and does not resolve the fundamental mystery of how life begins. If the origin of life is genuinely rare, occurring perhaps only once per galaxy or even less frequently, then the Fermi Paradox resolves itself. The galaxy is silent because life itself is the great filter, the improbable step that almost never occurs. Earth would then represent an extraordinary exception, a place where chemistry happened to cross the threshold into biology through a combination of circumstances unlikely to be repeated elsewhere. This possibility is both humbling and isolating, suggesting that the spark of life is far more precious and fragile than we might have imagined. Even after life emerges, the path to complexity and intelligence is not assured. Earth's history demonstrates that life can exist for billions of years in relatively simple forms, and that the transition to complex multicellular organisms requires overcoming significant challenges. One of the most dramatic events in Earth's history occurred approximately 2.4 billion years ago, known as the Great Oxidation Event. Photosynthetic bacteria had been producing oxygen as a waste product for hundreds of millions of years, but this oxygen was initially absorbed by dissolved iron in the oceans and minerals on land. Eventually, these oxygen sinks became saturated and oxygen began to accumulate in the atmosphere. For most life forms at the time, oxygen was a toxic poison. The Great Oxidation Event caused a mass extinction, wiping out many species that had thrived in the oxygen-free environment. The planet essentially poisoned itself through the metabolic activity of its own inhabitants. This crisis could have ended complex life before it began. However, some organisms adapted to the new oxygen-rich environment and even learned to harness oxygen for more efficient energy production. This adaptation eventually led to the evolution of complex cells and multicellular life. The transition was neither quick nor guaranteed. It took another billion years after the Great Oxidation Event before complex multicellular organisms appeared in the fossil record. This long delay suggests that the pathway from simple cells to complex organisms is not straightforward. It requires not only the right environmental conditions, but also unlikely evolutionary innovations. On other worlds, similar crises might not resolve so favorably. A planet's life forms might poison their environment and fail to adapt, leading to extinction or stagnation at a microbial level. The balance between environmental change and evolutionary adaptation is delicate. Too much change too quickly, and life cannot keep pace. Too little change, and there is no selective pressure driving complexity. Earth's history suggests that the path to complex life requires threading a narrow corridor between these extremes, and that many worlds with simple life might never develop the complex organisms necessary for intelligence to eventually emerge. Some scientists argue that Earth is not merely fortunate, but extraordinarily rare in possessing the specific combination of characteristics necessary for complex life. The rare Earth hypothesis proposes that while simple microbial life might be common in the universe, the conditions required for complex multicellular organisms and eventual intelligence are so specific that few planets possess them. Earth orbits a G-type main sequence star, a relatively stable and long-lived stellar type that provides consistent energy output for billions of years. More massive stars burn too quickly, not allowing sufficient time for complex life to evolve. Smaller stars are more stable, but prone to violent flares that could strip away planetary atmospheres. Our planet orbits within the habitable zone at just the right distance for liquid water to exist on the surface. Slightly closer, and Earth would have suffered a runaway greenhouse effect like Venus. Slightly farther, and it would be frozen like Mars. Earth has a large moon, formed by a massive collision early in the solar system's history. This moon stabilizes Earth's axial tilt, preventing extreme climate variations that might make complex life difficult. The moon also creates tides that may have been important for the development of life in coastal environments. Our planet has plate tectonics, a geological process that recycles carbon and maintains a stable climate over geological timescales. Plate tectonics also creates diverse environments and drives evolution through changing conditions. Most planets may be geologically dead, lacking this crucial climate regulation system. Jupiter acts as a gravitational shield, its massive gravity deflecting many comets and asteroids that might otherwise impact Earth. While some impacts are beneficial for delivering water and organic molecules, too many would prevent complex life from gaining a foothold. Earth's magnetic field, generated by its liquid iron core, protects the surface from harmful solar radiation and prevents the solar wind from stripping away the atmosphere. Mars lost its magnetic field early in its history and subsequently lost most of its atmosphere, becoming the cold, dry world we observe today. The rare Earth hypothesis suggests that having all of these factors align is extraordinarily unlikely. Most planets might have one or two of these characteristics, but having them all simultaneously may be rare enough to explain the Great Silence. If this hypothesis is correct, then simple microbial life might be common in the universe, but complex life capable of developing technology and civilization might be confined to a tiny fraction of worlds, perhaps only a handful per galaxy. Our Sun is a relatively calm and stable star, but this tranquility is not universal among stellar types. Many stars, particularly red dwarfs, which are the most common stars in the galaxy, exhibit violent behavior that would make the development of complex life extremely challenging. Red dwarfs are small, cool stars that burn their fuel slowly, potentially providing stable energy for trillions of years. This longevity initially made them attractive candidates for hosting habitable planets. However, observations have revealed that many red dwarfs produce powerful stellar flares, sudden eruptions of energy and radiation far more intense than anything our Sun produces. These flares can temporarily increase a star's brightness by factors of 10 or more, bathing nearby planets in harmful radiation. For a planet in the habitable zone of a red dwarf, which must orbit very close to its dim star to receive enough warmth, these flares would be devastating. The radiation would damage or destroy complex organic molecules, making the origin and persistence of life difficult. Even if life managed to emerge during calm periods, repeated flares might reset the evolutionary clock, preventing the development of complexity. Additionally, planets in the habitable zones of red dwarfs are likely tidally locked, with one side permanently facing the star and the other in eternal darkness. This configuration creates extreme temperature differences and unusual atmospheric dynamics that might not be conducive to life as we know it. Our Sun, by contrast, is remarkably stable. Solar flares do occur, but they are relatively mild and infrequent, compared to the violent outbursts of smaller stars. This stability has allowed life on Earth to develop over billions of years without facing repeated extinction-level radiation events. If most stars are red dwarfs, and most red dwarfs are too violent to host complex life, then the number of truly habitable worlds in the galaxy might be far smaller than estimates based purely on the presence of planets in habitable zones. The quiet nature of our Sun might be another rare characteristic that makes Earth special. The galaxy might be full of planets, but most of them orbit stars too violent to allow the slow, steady development of complexity that intelligence requires. This would help explain the silence, as the subset of stars calm enough to host complex life might be a small minority of the total stellar population. One of the most intriguing solutions to the Fermi Paradox is the Aestivation Hypothesis, which proposes that advanced civilizations are not absent but sleeping, waiting for a more favorable time in the universe's future. The hypothesis is based on thermodynamics and computational efficiency. All computation generates waste heat, and the efficiency of computation improves as the ambient temperature decreases. In the current era of the universe, the cosmic microwave background radiation maintains a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. While this seems cold, it will become much colder in the future. As the universe continues to expand, this background temperature will decrease, approaching ever closer to absolute zero over trillions of years. An advanced civilization that has solved its immediate survival needs and achieved effective immortality through technology might calculate that the most efficient strategy is to enter a state of hibernation, storing themselves in some form of stasis and waiting for the universe to cool. In the far future, when the temperature is a tiny fraction of what it is today, they could awaken and perform vastly more computation with the same amount of energy. The gains would be exponential. Waiting 1 trillion years would allow them to perform orders of magnitude more computation than they could in the current era. For a civilization that thinks on cosmic timescales, this would be a rational choice. They would essentially be sleeping through the high-energy, high-temperature youth of the universe, waiting to awaken in the cold, efficient future. This hypothesis elegantly explains the Fermi Paradox. The galaxy is not empty, but the civilizations within it are dormant, their automated systems maintaining minimal operations, while the vast majority of their computational resources remain offline, waiting. We would not detect them because they are deliberately minimizing their energy expenditure and electromagnetic emissions. They have no need to explore, expand, or communicate during this waiting period. Everything they want to do can be done more efficiently in the future, so they simply wait. The Aestivation Hypothesis reframes the Great Silence not as absence, but as patience. The universe is not empty, but sleeping, a cosmos in hibernation, waiting for winter to deepen before the real activity begins. From this perspective, humanity has simply awakened early, emerging into a galaxy where everyone else has already gone to bed, leaving us to wander the quiet halls of a sleeping civilization until we too learn the wisdom of waiting for a colder, more efficient future. Another possibility for why we do not observe expanding civilizations is that advanced societies might not expand outward at all, but inward into virtual realities of their own creation. The concept of a Matrioshka brain, named after Russian nesting dolls, describes a megastructure built around a star, consisting of layers of computational elements that harvest the star's energy to power vast simulated realities. An advanced civilization might conclude that physical exploration of the galaxy is inefficient compared to exploring computational spaces. Why travel to distant stars when you can create unlimited universes within sophisticated simulations? The computational power available from a single star, if fully harnessed, would be sufficient to simulate entire civilizations, worlds, and experiences far beyond what physical reality could provide. Such a civilization would turn inward, focusing on experiences within their created realities rather than expansion through physical space. From the outside, a Matrioshka brain might be detectable as an infrared source, the waste heat from its computation radiating into space. However, if the civilization is efficient and the structure is optimized, it might be difficult to distinguish from natural phenomena. We might be looking at such structures without recognizing them for what they are. The appeal of virtual existence is compelling. Physical bodies are fragile and limited. Virtual existence allows for experiences impossible in the material world. The ability to modify one's own consciousness, to experience time at different rates, to explore mathematical and abstract spaces that have no physical equivalent. For a civilization that has mastered the technology, the simulated realm might offer more genuine freedom and possibility than the physical universe ever could. This solution to the Fermi Paradox suggests that the galaxy might be full of civilizations, but they are all living inside computational structures around their home stars, having no interest in physical expansion. They are not broadcasting signals because they are not looking outward at all. Their attention is focused inward on the infinite possibilities of their created realities. From our perspective, they would appear as stars with unusual properties, perhaps slightly dimmed by surrounding structures, perhaps emitting excess infrared radiation, but not obviously artificial unless we knew precisely what to look for. The cosmos would be populated but silent, each civilization lost in its own computational dreams, indifferent to the physical universe and to potential neighbors who might also be dreaming their own separate dreams around distant stars. The dark forest hypothesis presents a more somber explanation for the Great Silence. It proposes that the galaxy is indeed full of civilizations, but they remain deliberately silent because revealing one's presence is dangerous. The hypothesis draws its name from the image of a dark forest at night. Each civilization is like a hunter moving quietly through the trees, aware that other hunters are present but unable to determine their intentions. In such an environment, the safest strategy is to remain silent and hidden. Broadcasting one's location would be an act of extraordinary risk. The logic proceeds from several assumptions. First, survival is the primary goal of any civilization. Second, civilizations cannot be certain of other civilizations' intentions. Third, due to the vast distances and time delays in communication, misunderstandings are likely and trust is difficult to establish. Fourth, the technological gap between civilizations might be enormous, making conflict asymmetric and potentially existential. Under these conditions, a civilization that detects another faces a dilemma. They cannot know if the other is friendly or hostile. They cannot know if the other is more or less advanced. They cannot know if the other will view them as a threat or a resource. The safest option, from a purely survival-oriented perspective, is to eliminate the potential threat before it becomes dangerous. This creates a grim equilibrium. Every civilization knows that revealing itself might trigger preemptive destruction from a more advanced neighbor. Therefore, every civilization remains silent, observing but not transmitting, listening but not responding. The galaxy becomes a dark forest where every civilization is both a potential predator and potential prey, and silence is the only rational strategy for survival. This hypothesis would explain why we detect no signals. It is not that civilizations are absent or technologically incapable of communication, but that they have learned through bitter experience that broadcasting is suicidal. Perhaps younger civilizations that announced themselves were destroyed by older, more cautious ones. Perhaps the galaxy has been shaped by a long history of conflict that has selected for silence and concealment. From this perspective, humanity's broadcasts into space, our radio and television signals leaking into the cosmos, our deliberate messages to the stars, might be acts of profound naivety. We are children calling out in the dark forest, unaware of what might be listening. The great silence might not be an absence, but a held breath. The galaxy waiting to see if we are wise enough to stop shouting before something hears us and decides we are a threat worth eliminating. A more benevolent explanation for the silence is the zoo hypothesis, which proposes that advanced civilizations are aware of humanity but have chosen not to make contact. We are being observed but not interfered with, like animals in a nature preserve or subjects in a long-term study. This hypothesis assumes the existence of a galactic community, or at least a consensus among advanced civilizations, that emerging species should be left alone to develop naturally. Contact might be considered harmful, potentially disrupting our natural, cultural, and technological evolution. Perhaps there are protocols, a cosmic version of the Prime Directive from science fiction, that forbids interference with pre-contact civilizations. The reasons for such a quarantine might be ethical, scientific, or practical. Ethically, advanced civilizations might believe that every species has the right to develop according to its own nature, without external influence. Scientifically, we might be more valuable as a natural experiment, a chance to observe how intelligence and technology develop independently. Practically, contact with a vastly more advanced civilization might be psychologically devastating for the less advanced species, potentially leading to cultural collapse or dependence. Under this hypothesis, the silence is deliberate and maintained. Advanced civilizations carefully avoid detection, ensuring that their presence does not contaminate our development. They might have technologies that allow them to observe us without being seen, or they might simply be patient enough to watch from a distance, waiting for us to reach some threshold of maturity before revealing themselves. The threshold for contact might be technological, such as the development of faster-than-light travel, or social, such as the achievement of global cooperation and the elimination of warfare. Until we reach this threshold, we remain in quarantine, isolated not by absence, but by deliberate policy. This explanation is comforting in some ways. It suggests we are not alone, but rather surrounded by older, wiser civilizations who are watching over us with benevolent interest. However, it also raises questions. How long might such a quarantine last? What criteria would trigger contact? And perhaps most troubling, what if we never meet the criteria? What if the threshold for contact is so high that most civilizations never achieve it, remaining in permanent isolation, not because they are alone, but because they are deemed unready for the larger galactic community? The zoo hypothesis transforms the great silence from a mystery of absence into a mystery of presence, suggesting that the quiet we experience is not natural but carefully maintained, a silence imposed by others for reasons we can only guess at from within our cosmic enclosure. Some theorists propose that sufficiently advanced civilizations might leave the physical universe entirely, transcending into realms or dimensions beyond our ability to detect or comprehend. The Transcension Hypothesis suggests that technological development follows a predictable trajectory that eventually leads away from the material world. As civilizations advance, they might discover ways to exist that do not require physical bodies or even physical space. They might upload their consciousness into substrates that exist in different dimensional frameworks, or they might discover that reality has layers or aspects that we cannot currently perceive. Black holes have been proposed as possible gateways to such transcendent states. The extreme physics near a black hole's event horizon might allow for forms of existence impossible in normal space-time. An advanced civilization might choose to enter a black hole, not as destruction, but as a transition to a new mode of being. Alternatively, they might create artificial universes, pocket dimensions where physical laws can be customized to their preferences. Why remain in a universe with fixed constants and limitations when you could inhabit one designed specifically for your needs? The appeal of Transcension is that it offers a solution to physical limitations. The speed of light limits how quickly information and matter can travel through space, making galactic colonization slow and expensive. But if consciousness can exist in non-physical forms, these limitations might not apply. The civilization could expand into computational or dimensional spaces where distance has different meanings or does not exist at all. From our perspective, such transcended civilizations would be completely undetectable. They would leave behind their physical infrastructure, perhaps allowing it to decay or be reclaimed by natural processes. The galaxy would appear empty of intelligence, not because intelligence is rare, but because intelligence naturally evolves beyond the physical stage we currently occupy. This hypothesis suggests that the Great Silence is a consequence of our developmental stage. We are looking for civilizations in physical space because that is where we exist, but advanced civilizations have moved beyond physical space into realms we cannot yet access or even properly conceptualize. The universe might be full of transcended intelligence, but it exists in a layer of reality orthogonal to our own, invisible to our instruments, and perhaps even to our categories of thought. We are like fish in the ocean, searching for other fish, unaware that the land above us is populated by creatures who have left the water behind entirely. One of the most profound possibilities is that we are not late to the cosmic party, but early. The Firstborn hypothesis proposes that humanity might be among the first technological civilizations to arise in the Milky Way, or possibly the very first. While the universe is 13.8 billion years old, conditions suitable for complex life have not always existed. The first stars contained only hydrogen and helium, lacking the heavier elements necessary for planets and life. These elements had to be forged in stellar furnaces and distributed through supernovae. It took several generations of stars living and dying before the galaxy was enriched with enough carbon, oxygen, nitrogen, and other elements to make Earth-like planets possible. Additionally, the early universe was more violent. Supernovae and gamma-ray bursts were more common, potentially sterilizing planets before life could gain a foothold. Active galactic nuclei poured radiation across vast regions of space. Only in the last few billion years has the galaxy calmed enough for life to develop without frequent extinction-level events. Earth formed 4.6 billion years ago, relatively late in cosmic history, but perhaps early in the window of habitability. If the conditions necessary for complex life only recently became common, then most potentially habitable planets might be younger than Earth, still in their microbial stages, or not yet having developed life at all. We might be among the first to cross the threshold into technological civilization simply because we had a head start, forming around one of the earlier second-generation stars in a calmer region of the galaxy. This possibility is both exciting and sobering. If we are first, then the galaxy is ours to explore and settle. There are no ancient civilizations to guide or threaten us. The future of intelligence in the Milky Way might depend on the choices humanity makes in the coming centuries. We carry a tremendous responsibility as potential ancestors to a galactic civilization. However, being first also means being alone. There is no one to learn from, no one to contact, no one to provide reassurance that the challenges we face are surmountable. We must figure out how to survive and thrive without guidance, hoping that we can avoid the pitfalls that might have claimed other potential first civilizations in other galaxies. The Firstborn hypothesis transforms the great silence from a mystery into a responsibility. The galaxy is quiet because we arrived before anyone else could make noise. The question is whether we will survive long enough to greet the second civilization to emerge, or whether we will fall silent ourselves, leaving the galaxy to wait for the next species to try their hand at becoming spacefaring. If we are alone in the galaxy, or even if we are simply the first or one of very few technological civilizations, the implications for humanity are profound. Life becomes precious in a way that is difficult to fully articulate. We are not merely one species among millions on Earth, but potentially the only conscious observers in billions of cubic light-years of space. The responsibility this entails is staggering. Every extinction we cause, every ecosystem we destroy, every species we drive from existence represents a loss not just for Earth, but for the cosmos. If life is rare, then Earth is a treasure beyond measure, a garden of biological diversity in a desert of sterile worlds. The choices humanity makes in the coming centuries might determine whether consciousness persists in this region of the universe or falls silent. Our current trajectory includes significant risks. Climate change threatens to destabilize the systems that support civilization. Nuclear weapons remain capable of destroying technological society. Emerging technologies like artificial intelligence and biotechnology carry both promise and peril. The same tools that might allow us to flourish could, if misused, lead to our extinction. Yet there is also cause for hope. Humanity has demonstrated remarkable resilience and ingenuity. We have overcome challenges that seemed insurmountable. We have developed technologies that have improved quality of life for billions. We have begun to understand our place in the cosmos and the fragility of our planetary home. The responsibility of being alone, or nearly alone, might itself be a source of meaning and motivation. If we are the universe's way of knowing itself, as the astronomer Carl Sagan suggested, then our survival and flourishing become cosmically significant. We are not merely trying to preserve our own species, but safeguarding the possibility of understanding, compassion, and beauty in a universe that might otherwise be devoid of these qualities. This perspective does not require certainty about our uniqueness. Even if other civilizations exist, they are far enough away that we cannot rely on them. We must take responsibility for our own survival and for the preservation of life on Earth. The great silence, whatever its cause, teaches us that consciousness is not guaranteed to persist. It can be lost. It can end. The fact that we have not detected other civilizations suggests that the path from emergence to long-term survival is narrow and fraught with dangers. Many species might reach our level of development only to fail in the next steps. Our task is to be among those who succeed, to become a civilization that endures not just for centuries, but for millions of years, spreading life and consciousness through a galaxy that desperately needs it. When radio telescopes scan the sky, searching for signals from distant civilizations, they detect the cosmic microwave background radiation, the echo of the Big Bang itself. This faint whisper fills the universe, a reminder of the moment when space and time began. The cosmic microwave background is remarkably uniform, varying by only tiny fractions of a degree across the entire sky. These minute variations represent the seeds of all structure in the universe, the quantum fluctuations that eventually grew into galaxies, stars, and planets. Listening to this ancient signal is a form of meditation on cosmic time. The photons that compose the cosmic microwave background have been traveling for 13.8 billion years, since the moment the universe became transparent to light. They have crossed the entire observable universe to reach our telescopes, carrying information about the earliest moments of existence. In a sense, we are looking back in time, observing the universe as it was in its infancy. This echo is the only signal that fills the entire universe. It is the baseline against which all other signals are measured. When SETI searches for artificial transmissions, they are looking for deviations from this background, for patterns that stand out against the cosmic static. The fact that the background is so uniform, so predictable, makes the absence of other signals more noticeable. If the galaxy were full of broadcasting civilizations, their signals should be detectable above this background hum. Yet the universe remains dominated by natural processes, by the predictable emissions of stars and galaxies, by the ancient light of the Big Bang itself. There is something peaceful about this realization. The universe does not need artificial signals to be interesting. The natural phenomena we observe, pulsars and quasars and colliding galaxies, are spectacular enough without technological augmentation. The cosmos tells its own story through the language of physics, and that story is profound. The cosmic microwave background reminds us that we are part of something much larger than ourselves or our civilization. We are made of atoms forged in stars, arranged in patterns that allow us to contemplate the universe that created us. The echo of the Big Bang is not just a signal to be detected, but a connection to the origin of everything we know. Listening to it is a way of touching the beginning of time, of experiencing the universe not as a collection of separate objects, but as a unified whole, a single process unfolding across billions of years. The search for extraterrestrial intelligence is fundamentally an exercise in patience. Even if civilizations are common in the galaxy, the distances and timescales involved mean that contact might not occur for thousands or millions of years. Radio signals travel at the speed of light, which seems fast until confronted with the vast distances between stars. A signal from a civilization 1,000 light-years away would take 1,000 years to reach us, and our reply would take another 1,000 years to return. A single exchange of messages would span 2 millennia, far longer than recorded human history. For more distant civilizations, the delays become even more extreme. A conversation with a civilization on the opposite side of the galaxy would require 100,000 years per exchange. Such communication would not be a dialogue, but a series of messages sent into the future, hoping that someone will still be listening when they arrive. The timescales of the cosmos are humbling. Civilizations might rise and fall in the time it takes for a single message to cross the space between stars. We might send a signal to a thriving civilization, only for it to arrive at a dead world, the recipients having gone extinct millennia before our message reached them. Or we might receive a signal from a civilization that no longer exists, a ghost voice from a species that flourished and fell silent long before their message reached our telescopes. This temporal disconnect means that even if the galaxy is full of civilizations, they might be effectively isolated from each other, separated not by space alone, but by time. Each civilization exists in its own temporal bubble, able to observe the past of others, but never able to interact with their present. The long wait is not merely about waiting for contact, but about accepting that contact might never come, or might come so far in the future that we cannot imagine what humanity will be like when it happens. It requires a shift in perspective, from expecting immediate results to thinking on generational and civilizational timescales. The search for extraterrestrial intelligence becomes not a project with a defined endpoint, but a continuous process, a commitment that extends beyond any individual lifetime or even any single era of human history. Yet there is value in the waiting itself. The search forces us to think about our place in the universe, to consider what it means to be intelligent and technological, to reflect on what we would want to say to another civilization if we had the chance. The process of searching changes us, making us more thoughtful, more humble, more aware of the vastness that surrounds us and the preciousness of the consciousness we possess. In the darkness of the cosmos, Earth shines like a single candle. Our planet is a small world orbiting an ordinary star in an unremarkable region of the galaxy. Yet it is the only place we know of where life exists, where consciousness has emerged to contemplate the universe. The image of a candle in the dark captures something essential about our situation. A candle provides light, warmth, and the possibility of seeing what lies nearby, but it does not illuminate the entire room. Beyond its small circle of radiance lies darkness, vast and unknown. We cannot see what else might be out there, whether other candles burn in distant corners or whether we are the only light in an empty hall. The candle metaphor also suggests fragility. A candle can be extinguished by a careless wind, by lack of fuel, or by the passage of time. It must be tended and protected if it is to continue burning. Earth's biosphere is similarly fragile, dependent on a narrow range of conditions, vulnerable to disruption. Our technological civilization is even more delicate, requiring not just physical survival, but the maintenance of complex social and economic systems that could collapse under sufficient stress. Yet a candle also represents hope and defiance. To light a candle in darkness is an act of courage, a statement that the darkness will not have the final word. Even a small flame pushes back the shadows, creating a space where warmth and light can exist. Humanity, for all our flaws and limitations, represents such a flame, a conscious presence in a universe that might otherwise be unconscious, a source of meaning in a cosmos that does not inherently provide any. The great silence, from this perspective, is not a problem to be solved, but a context to be accepted. We may be alone, or we may be one of many candles scattered so far apart that we cannot see each other's light. Either way, our task remains the same: to keep our candle burning, to protect the fragile flame of consciousness and life, to ensure that this small light continues to shine into the darkness for as long as possible. Perhaps someday we will discover other candles, other civilizations who have also persisted through the challenges of existence. Perhaps we will remain alone, the only light in our corner of the galaxy. But regardless of whether we are solitary or accompanied, the value of our light does not diminish. A single candle in an empty room is not less meaningful for being alone. It is, if anything, more precious, more worthy of protection, more deserving of our care and attention. The great silence teaches us that consciousness is rare, that intelligence is precious, that the universe does not guarantee our survival or success. We must earn our persistence through wisdom, cooperation, and care for the world that gave us birth. We have journeyed through the quiet corridors of the Fermi Paradox, exploring the mathematics of loneliness, the filters that make complexity rare, and the various explanations for why the cosmos remains so profoundly silent. The great silence is not a single mystery, but a collection of interconnected questions about life, intelligence, and our place in the universe. Each potential solution offers its own perspective on existence. Perhaps we are alone, the first or only civilization in our galaxy, carrying the responsibility of being consciousness's sole representative in this region of space. Perhaps we are surrounded by others who remain deliberately hidden, either sleeping through the current epoch to await a more efficient future, lost in virtual realities of their own creation, or carefully concealing themselves in a dangerous galaxy where revelation means risk. Perhaps the path to intelligence is so narrow, so fraught with filters and challenges, that very few worlds ever produce technological civilizations. Or perhaps intelligence is common but fleeting, with most civilizations falling silent shortly after achieving the ability to communicate across the stars. We do not yet know which explanation is correct, and it is possible that multiple factors contribute to the silence we observe. The universe is under no obligation to make its mysteries easy to solve or its answers comforting to hear. What we do know is that Earth is precious, that life is remarkable, and that consciousness represents something genuinely special in the cosmos. Whether we are alone or accompanied, rare or common, first or late, these facts remain true. The Great Silence invites us to reflect on what matters. It asks us to consider our responsibility to the biosphere that produced us, to the future generations who will inherit the consequences of our choices, and to the possibility of consciousness itself persisting in a universe that does not guarantee its survival. As we drift toward rest, we can take comfort in the peaceful nature of this mystery. The silence is not hostile but neutral, not threatening but simply present. The universe continues its slow unfolding, galaxies turning in the dark, stars being born and dying, planets orbiting in the quiet. We are part of this process, temporary arrangements of matter that have become aware of themselves and their surroundings. If you found this exploration calming and would like to continue these journeys through cosmic mysteries, consider staying with us for future videos. We will continue to explore the universe's gentle questions, always with the goal of providing interesting content that soothes rather than agitates, that invites contemplation rather than anxiety. The cosmos is vast, and there are many more quiet mysteries waiting to be explored together. For now, rest well, knowing that whether we are alone or accompanied in this universe, we are part of something ancient, beautiful, and worthy of wonder.